Thank you, Anita, and thank you for inviting me today. It's a really exciting event. I've enjoyed the talks that I've seen so far. I hope you're still awake after the lunch break. So I'm Professor of Health Informatics at the University of Manchester. I've got a background in computer science and AI, and I'm going to talk about risk prediction models for healthcare today. So let me give you a brief overview of my talk. So we're going to start with looking at the data revolution in health, just a couple of slides on what's happening in terms of big data and all the opportunities that we have nowadays in healthcare. Then we're going to talk about predictive analytics. That's going to be the meat of my talk. I'm going to look at one question that people always ask. Is machine learning better than statistical modeling for health risk prediction? Then we're going to look at causal prediction models, at prediction with electronic healthcare records, and I'm going to end with a summary and conclusions. So the data revolution in health, if you look at where we come from and where we are now, and this has happened in, less than 3 decades really, all we knew about health previously came from data obtained in research studies like clinical trials, observational cohort studies, etc. Nowadays, there are so many more opportunities to understand and study health using, for instance, omics data, biological data, routine healthcare data, which we will talk about today, home-based sensors, so smart weighing scales, for instance, that people use at home, but also smartphones are a source of health data and wearable sensors. So there's tremendous opportunities nowadays to study health, way more than we ever had. So this is basically the most exciting time to be a health researcher, I think. But it's also very challenging for data scientists, because all these data are fundamentally different than those traditional research data. So we have to adapt our methods, and that's what part of my talk will address. So all these data, what do they allow us to do? Well, broadly speaking, they allow us to get a more comprehensive picture, a better picture of the 3 pillars of medicine. The first of which is the biology. So the genome, transcriptome, proteome, all those omics. The second pillar is what we call the exposome, the things that we are exposed to and would influence our health. So that's the environment that we live in, but also our own behavior that is related to health. And also treatments that we get when we go to a doctor. And finally, there's the phenome, the way that health and disease manifest itself. And if we can link those 3 pillars together, we get a comprehensive picture of the things that determine health and disease, the phenome. And through all those data that I showed you on the previous slide, I think the opportunities to do that are now better than ever. So a number of very grand visions have been formulated about what we can achieve now with this better picture. And one of them is called P4 medicine. So that's for medicine that tries to predict what's going to happen before people actually get ill, prevent that would actually happen, do that in a very personalized way, and engage people so they become active participants in their health and care. So that's P4 medicine, and it was formulated by this person here, Leroy Hood. And many people see this as the vision for medicine as it should be in the future. Another grand vision is that of what we call learning health systems. So these are healthcare systems that improve continuously using data that they generate themselves. So every time we go to the doctor, obviously, some data will be collected and stored in an electronic health record. Obviously, we can use that data to learn from and provide better care. So that's a learning healthcare system, and it typically uses that cycle that you see over there. So in Manchester, we work with the National Institute for Data Science and AI in the UK, the Turing Institute. And I'm going to talk to you a little bit about the work that we do with the Turing Institute. So that institute was established in 2015, 4 years ago, by 5 universities. Later on, 8 other universities joined, including Manchester. They have headquarters in London at the British Library. And broadly speaking, the Turing Institute has 3 broad aims. So the first is to advance world-class research and apply it to real-world problems like health. The second is to train the leaders of the future in data science and AI. And the third one is to lead the public conversation about data science and AI. And I think that third one is actually very important because, as you're well aware, and it's not different here in France as anywhere else, this is now something that is in the public debate, and many people write and think about it. Many people have concerns actually about what AI is going to do to our society, including what it's going to do to healthcare. So that's very important, I think. So the Turing has programs in data science at scale, so data science with very, very large data sets, in defense and security, finance and economics, and health and medical science, as well as a number of other programs. But these are the most important ones. So what do we do in Manchester? So we've got about 14 people working as a liaison to the Turing, 10 of which are so-called Turing Fellows. I'm one of them. And we've got an extensive program in health, which is led by myself, with 3 projects. So the first is predictive healthcare, which we're going to talk about today. And then we've got a project in patient subgroup discovery and in human-centered systems. So we're going to talk about clinical prediction models. Let me start with a definition. So clinical prediction models are mathematical equations or algorithms which take information from an individual patient as inputs and then produce an output, which is a prediction, usually probability, regarding that patient's either prognosis or diagnosis. So an example could be we take a patient's age and sex and we predict their risk of developing heart disease, cardiovascular disease within the next 10 years. And actually, there are models that do that. They use a little bit more than age and sex. And we're going to see an example of that shortly. So clinical prediction models are a form of what we call supervised learning, and most of you will be familiar with that. So in a supervised learning, we've got training data that we use to develop a model, which is called the build phase, using some kind of estimator algorithm. And then once we have that model, we can then use it to make predictions for new data, in this case, from new patients that we see, for instance, in our clinic. So broadly speaking, there are 2 types of clinical prediction models, ones that are used for diagnosis and ones that are used for prognosis. We're going to focus on the ones that are used for prognosis today. So the ones that are used for diagnosis try to predict the current state of affairs for an individual, things that are already happening, so their diagnosis, for instance. Prognostic clinical prediction models predict the likelihood of something that hasn't happened yet. So something that is going to happen, might happen in the future. So that could be some kind of clinical event. It could be disease recurrence or progression of disease or some kind of outcome. So typically what we have in these prognostic models is some time point 0, which we typically call baseline. And from that baseline, from what we know at baseline, we're going to look at the exposures at that moment in time and predict the risk of something happening at some point, predefined point in the future. So just a couple of typical applications of clinical prediction models. So in the diagnostic models, we would use them for screening for disease, for instance, and for triage. So triage are models. Triage is needed in, for instance, emergency care settings, where we need to define which patients need care the most urgent and which ones could wait a little bit longer. And for that, there are models that help you to do that, make those decisions. Today, we're going to focus on prevention, and that fits within that concept of P4 medicine. So prognostic models are used in acute care, cancer recurrence, and chronic disease. So in acute care, we're typically talking about up to 30 days, so people who are in the hospital, and very often actually about very short time windows, like 48 hours. When we talk about disease recurrence, cancer recurrence typically, we talk about 1 to 5 years. And when we talk about chronic diseases, we try to predict 5 to 10 years ahead. So when we focus on chronic disease, we typically talk about cardiovascular disease and other long-term conditions. I'm going to use an example from a model that's used in the UK, which is called QRisk, and which is recommended by the clinical practice guidelines and has been implemented in all the general practices in the UK. So all the general practices use this model because it is also something that the guidelines say that they have to do. So I'm actually going to try to switch to a browser rather than showing you these screenshots. So let me see if I can do this. Okay. So now okay. We're going to go for the fallback option. Let's go for the fallback option. No internet connection. So here's a system. I would recommend that you Google for QRisk and try it yourself. This is a freely available system. And what it does is it allows you to enter your individual characteristics or from someone else, and then it will provide the risk that that person will have a heart attack or a stroke in the next 10 years. You can actually vary the timelines, but 10 years is typically what we use. So in the example here, I've said we're looking at someone who's 50 years old, who is a male, and that person is not a smoker. He has got type 2 diabetes, and he's also on current blood pressure treatment, so taking medication for hypertension, blood pressure. I've left most of the other things blank, which basically means no. Then here there's a couple of values that I also left blank because I didn't know them, but here they mean actually don't know. And finally I gave body height and body weight, and this person is overweight. So they're 1.78 meters and they weigh 95 kilograms. So what QRisk then does is come up with an estimate of the risk that that person has a heart attack or a stroke within the next 10 years. In this case, it's 12.4%, which is pretty high actually. It's also visualized, so the blue unhappy faces all get a heart attack or a stroke and the others do not. And this is also above the guideline recommended threshold for treatment with statins. So the English guidelines would now say this person needs to be treated because their risk is higher than 10%, and treated with statin medication. So, yes?
Is this thing government approved?
Sorry?
Is this thing government approved? You can go and you can check self-diagnose yourself.
Uh-huh.
People are okay with that? The government says fine?
Yeah. So the question is whether this is government approved. It is. So it has been approved by NICE, which is the National Institute for Clinical Excellence in the UK. And yes, it is an open system, so everyone can do this and calculate their risk.
And have people thought about the social consequences?
Yeah, it's a good question actually. I'm not aware of anyone who's looked at that. And so you're right that interpreting this kind of risk information that we saw here is obviously can be challenging, and it can also create distress. And yes, it could happen that people use this system and panic because of the results. Yes?
And the people who designed the system, they must have thought about the issue, right?
So the question is, the people who designed the system must have thought about this. I'm not sure, to be honest. And I think that's perhaps related to one of the challenges I find of my field, is that there are statistical challenges, epidemiological challenges, informatics challenges, computer science challenges, but also behavioral challenges or psychological challenges. Now, the people who work on these things come from very different backgrounds typically, and sometimes they don't work together.
And I'm not big on saying everything is ethical, but there's a big ethical challenge there, right?
Yeah, I mean, I think this system was developed by epidemiologists who basically looked at the data and said, this is the correct model. So what could be wrong with it? But you're right that from a psychological perspective, it could perhaps not be a good idea to give this to everyone, make it available to everyone. Thanks. So this system is based on a statistical technique called logistic regression, which basically does the following. We try to estimate the probability that some variable is 1, variable y. So y is 0 means everything's okay. Y is 1 means trouble. In this case, it means heart attack or a stroke. Given information that we have represented by x, if we have just one variable, we would have a linear equation, alpha plus beta times x, and that is put through the logistic transformation, which is 1 divided by 1 plus e to the power minus that equation. If we have more than one variable, like in the Q-risk model, we would have x1 through xm, and that becomes a weighted summation in the formula. Another way to write this is as follows. Here we express the probability, the conditional probability, as an odds. So by taking p, the conditional probability that y is 1 given x, and dividing it by 1 minus that probability, we get the conditional odds, which is just the same thing expressed on a different scale. And then if we take the log of that, that would equal alpha plus beta times x. So this is basically how logistic regression works, and it's very simple, as you can see. A little bit of mathematics, a little bit of probability theory, a little bit of algebra, and there you have your model. So let me give you an example of how this works in practice. Not the Q-risk model, but I'll use a different model, which is called Apache, and it's used in critical care, intensive care. And this model actually has only 3 variables. One which represents a score ranging from 0 to 71, and which indicates how severely ill the patient is. Then a diagnosis, which is categorical and has 54 different categories, different diagnoses. And then finally, a binary variable, u, which is 0 or 1, which represents urgent surgery. So this is the formula for Apache. So this is the conditional log odds of death in this case, because the model predicts death. And these are the 57, this is the formula with 57 coefficients that are estimated from data. What this looks like is as follows. So all logistic regression models have this typical S-shaped curve ranging from probability 0 to 1. And here we have 3 curves, one for people with a drug overdose, that's the green curve, one for people with pneumonia, and one for aortic aneurysm. Now, most people at the ICU would have a relatively low score. It's actually quite rare that people have a score higher than 25 or 30. So you can see in this range, the probability are not necessarily so high. So if you have a drug overdose, you will probably survive it. If you have an aneurysm, then things are quite different, but that's logical because having an aneurysm basically means you're bleeding to death from inside of your body. So most models that are used in practice, like QRisk and like Apache that we just saw, are based on this relatively simple form of statistical modeling. Many people ask, could we not better use machine learning than statistical models for predicting health risks? And people have experimented with this. So here, for instance, we see a decision tree. This one was actually developed by myself about 10 years ago to predict the risk of people developing post-traumatic stress syndrome after having experienced a life event. And you see that the structure of the model is very different. We don't have that equation. We have a tree structure and 5 risk groups. And there's also other forms of machine learning that you can use to do the same thing. So you can generalize this using random forests. You can use neural networks, support vector machines. So basically all the machine learning methods can be used to predict these kinds of risks. So the question is then, would they work better or not than statistical models? Now, one thing I think to keep in mind is that this, to some extent, this is a false dichotomy, as I would say, because the two fields are not completely separate, but they are essentially forming a single field, sometimes referred to as statistical learning, where different methods vary in terms of complexity. So some people would say that logistic regression is also a form of machine learning. The elastic net, which is a generalization of logistic regression, is by most people seen as a form of machine learning. And then gradient boosting and deep learning would be considered machine learning. But these methods are all very related in terms of the underlying maths and stats. They just differ in terms of complexity. Another way to look at it is represented here on the slide, and this comes actually from Robert Tibshirani, who's a famous statistician from Stanford. And he believes that this distinction between statistics and machine learning is all flawed, because he says it's one field, it's the same thing, they just use different terms. So for instance, in machine learning we say networks and graphs, and in statistics we say model. And in machine learning, we focus on prediction, whereas in statistics we focus on inference. What we call parameters in statistics are called weights in machine learning. And there's some other things like, a large grant would be 50K in statistics and about 1 million in machine learning. And they would also differ in the types, in the places where they would have a conference. But basically, Robert is saying here, it's all the same thing. And stop making that distinction because it's flawed.
Sorry. I think still there's a difference between the two, which is the notion of end-to-end on the machine learning side and feature engineering on the statistical side. Which doesn't appear here, which seems to me quite important.
Okay, could you repeat that?
Yeah, I think still that there is a big difference between the sides, which is captured by the keywords end-to-end on the machine learning side, and feature engineering on the statistical side, and they make, in my view, a big difference.
Yeah, I think I would agree, but I think what Robert Tibshirani is trying to say here is that emphasizing distinction is not helpful. And you're right that there are these differences in emphasis. I've got another slide which comes from the book by Itham Alpidin on machine learning. And he also says that there are differences in how people approach the same problem. So for instance, in statistics, we have an important role for the analyst, so that's feature engineering, which we wouldn't have in machine learning because there the goal is fully automated learning. Doesn't mean that we always achieve that goal in machine learning. Very often we do not. So then there would still be a role for the analyst, but there is a focus on trying to automate things in machine learning that we do not have in statistics. So I agree that there are differences, but I can see why people like Robert PSAI are arguing to not overemphasize the distinction, because mathematically speaking, it's the same field. Let me go back to the question that we had, which was, is statistical modeling or machine learning better to predict health risks? So some people have actually tried that, and here's a paper from colleagues of mine from Manchester who had a data set in burn injuries, and what they tried to do is predict whether the people with those burn injuries would die. So this was in acute care, and they used logistic regression, but also a number of different machine learning methods, like random forests, neural networks. What they found is actually that there was no difference in performance. So all models performed more or less the same. And they said in the end, for that reason, we will prefer the logistic model because it's the most transparent model, the one that we can most easily understand. Here's a study that aimed to predict urinary tract infections in the emergency department, and also compared logistic regression with a number of machine learning methods. In this case, actually, it was a machine learning method, XGBoost, which is a form of gradient boosting, which was clearly superior to the other methods, including logistic regression. So this model had much less false positives. Then earlier this year, a systematic review appeared where all these different studies that make such comparisons like the two that we just saw were summarized. And this was from a group across Netherlands, Belgium, and the UK. And they included 71 studies and looked at all the different comparisons between logistic regression and machine learning. In the end, they said, there is no difference. There is no evidence that through machine learning, we would get better predictions than with logistic regression. And I think given the number of studies, so 71, that's quite substantial, it doesn't seem very probable that machine learning is really going to beat logistic regression. So interesting result, and to some extent unexpected, because theoretically you would think, well, machine learning should be able to do better, but in practice it turns out that's not really the case. I'm going to switch to a different topic, just looking at where we are in terms of time, which is causal prediction models. And this is something that we've been working on in Manchester for the last few years. So here is Noah. Here he is. And Noah is the 3-year-old son of Matt. Matt's over there. Matt's one of my colleagues who leads on this piece of work. And the picture was taken close to where they live, which is in the countryside close to Manchester in the Peak District. You can see it's quite beautiful there. And here's a path close to their house where they walk frequently. And every now and then, it happens that a car needs to pass, because actually, further down this path, there are 1 or 2 houses. And the only way that people can get to those houses is using their 4-wheel drive to get there. It doesn't happen very often, but if it happens, Matt says to his son, Noah, stand to the side of the road so the car can pass, right? And after a while, when this had happened 1 or 2 times, he noticed that Noah started to drag him to the side of the road very often. And he was wondering what was going on until he realized actually that Noah, so like all 3-year-old boys, Noah is absolutely fascinated by cars. He thinks cars are the most cool thing in the world. And he thinks that if you stand to the side of the road, there will be a car, because that's what has happened a couple of times. So he's made an inference based on what he has observed. And it's a plausible inference, it's just unfortunately wrong, because this is not the actual structure of what's going on. The actual structure is this. When there is a car approaching, that will make 2 things happen. One is that both Matt and Noah will stand to the side of the road, and there will be a car that passes by. And because Noah wasn't aware of this causal structure, he made a wrong inference. So this can happen very often when we look at data. And sometimes it's obvious that we shouldn't interpret the risk model causally. So there's a famous study published in 2015 by Rich Caruana and colleagues, which looked at the risk of in-hospital death among patients with pneumonia. And what they found is that patients who also had asthma were less likely to die of pneumonia. Now that's really strange if you think about it, right? Because asthma is not a good thing, as far as I know. I'm a computer scientist, but I'm pretty sure that asthma is not a good thing. So if you have asthma, you're less likely to die of pneumonia. It doesn't make much sense. So after scrutiny of the model, and then after talking to various doctors that they worked with, they found out that all asthma patients that develop pneumonia will go to the ICU, the intensive care unit. And obviously, in the intensive care unit, they will get the best treatment. And therefore, the mortality rates among those patients are actually lower than among all other pneumonia patients that don't go to the ICU. So there's a good explanation, but the explanation has to do with causality. It has to do with treatment, because the ICU is actually a treatment. Interestingly, this model stirred a lot of discussion about explainability of models and how important it is. I think there's a lot to be said about this because, in fact, to understand what's going on here, you have to understand the hospital where the data were collected and the existing policies and procedures over there. So let's go back to the Q-risk model that we saw before. So this model is used by general practitioners, family doctors, when they see their patients. And very often what they do is, for instance, they have someone in front of them who's a smoker, and their risk will probably be quite high because smoking does induce heart attacks and strokes. And they then use this field and change it to non-smoker to show to the patient how their risk will drop if they stop smoking. Is that correct? I see people saying no. Why not?
Because it's history. So there is the length of time being a smoker should apply there.
Yes, you're right. So basically, if we change this field to non-smoker, what we're saying to someone, if you never had been a smoker, right, then your risk would have been this. But that's no longer achievable. You can't change history. What you only can do is stop smoking. But that's something very, very different. And that is something that the model can't tell us. We can only change this field, but it would basically say, let's try to change history. We can't do that. So there's a clear need here for people to be able to reason about what we call interventions, right? Changing smoking status. And the model doesn't allow us to, because it's based on logistic regression. It wouldn't be different if we would base it on machine learning. All these models are not capable of doing that. So what I would argue is that we need a new type of model that would help us to do exactly that. So what we have in the current model structure is that smoking is a risk factor for cardiovascular disease, CVD, and there are other risk factors as well. But the actual causal structure is that there are unmeasured confounders that influence both smoking and cardiovascular disease. So other lifestyle factors, for instance, people's education levels, where they work, where they live, all these things play a role both in whether they would smoke and whether they will have cardiovascular disease. And we can only properly model the effect of stopping smoking if we adjust for those unmeasured confounders. So people have looked in recent years about how treatment and interventions are being handled in prediction models. And not surprisingly, in most prediction model studies, the topic is largely neglected because we don't really have the methods to deal with it. So like I said, users are still very keen to explore these what-if scenarios. What would happen if this person would stop smoking? Or what would happen if we start treating them with statins today or with blood pressure lowering medication? So risk prediction methods should be extended with methods for counterfactual causal reasoning. Reasoning about cause and effect that goes against the actual facts, so counterfactual. I think in the interest of time, I'm going to skip a few slides and go to the second topic that I wanted to discuss with you, which is prediction with electronic healthcare records. So I mentioned in the beginning that electronic healthcare records are one of these big opportunities that we have nowadays in terms of data that previously weren't available but are available now and can be used within health research and for developing prediction models. So these data are typically larger and more representative of the population than any other type of data. But there are massive challenges. And the reason is that all the recordings in these databases are driven by transactions with the healthcare system. So they are very different than normal research data. There's usually variation in recording practice, in follow-up times. There's usually both structured data and unstructured data. So with unstructured data, we mean text and images. In electronic healthcare records, we only have so-called positive diagnostic codes. So we can have a code for diabetes, this patient has diabetes, but what we can't have is this patient doesn't have diabetes, that doesn't exist. And meaningful events are often not explicitly recorded. So what is recorded is that people have been prescribed medication, but the decision to stop doing that is not in the record. So many researchers have warned that these are not normal healthcare data. So if we want to use them, there's risks for all kinds of biases and mistakes. And there's now a growing body of literature about what happens if we ignore those biases. But there's still a lot of work to do, I think, for data scientists to develop methods that can properly adjust for those possible biases and or sometimes actually use the specific structure of electronic healthcare records. So one of the things that we focus on in Manchester is what we call informative observation processes. So here you see the records from 2 patients. And in the top record, we've got someone who actually died from a cardiovascular event, probably a heart attack or a stroke. And what we see actually that in the months, well, years actually, preceding that event, the number of blood pressure measurements went up. So clearly there was something going on, and probably the general practitioner of this patient's doctor, felt that it was necessary to do these measurements. At the lower end, we have another record, another person, and someone who at some point left the practice because they just moved, but they didn't die from an event. And what we see is that the frequency of these blood pressure measurements is much lower. So clearly, there is something about that measurement process that could help us to predict the event, because the doctor was aware of things going on that we might not see in the data. So these are called informative observation processes. A couple of years back, there was a review of all the studies that used electronic health records to develop prediction models. And it was found that across all those studies, very few studies actually use this type of informative observation process. There has been some work in this area, not specifically to risk prediction models. So here's a review of methods that use visit processes and the assumptions underlying them in statistical models. And if we think about what's happening in these informative observation processes, then typically we will have the recording of risk factors like the blood pressure that we saw in those 2 records, and then things that were not recorded but influence the recording of those risk factors. And these are risk factors that the doctor will have seen. So they might have seen, for instance, in small cues. So it might have been skin color, it might have been symptoms that the patient reported to them but that were not recorded. But they had reasons to change the frequency with which they made observations. And that's the reason why very often that frequency itself can then be predictive. So George Ripsack, who's a professor of biomedical informatics at Columbia University in New York, has actually argued that because of this, these complex observation processes, we should start a new field almost that studies the electronic health record in the way that we study natural sciences, physical sciences. So basically what George says, and this is a diagram from his paper, that what we see in the electronic health record is the substrate of very complex processes. And only if we start understanding all these complex processes, we can start to understand the substrate and draw inferences from it. This is very, very different than how people nowadays do research with electronic healthcare records, but I think he's absolutely right that we have to understand these processes. So before I finish, a couple of further challenges in this field of health risk prediction. So one of them is using longitudinal data. So in any healthcare record, we will always have longitudinal measurements, so data that were collected over time. Very few models actually use that data. So the Q-risk model that I showed you doesn't do that. Very few models do it. One of the challenges is that for some patients, the history will be very short and we will have very little information, whereas for others, it will be very rich. So it's hard to deal with that for any method, be it statistical or machine learning. Then the second challenge is dynamic risk prediction. So typically what we want to do is, as time progresses, make different predictions for the same individual. And their risk will change over time. A third challenge is what we call calibration drift. So as calendar time progresses, risks in the population will change, for instance, because medical practice changes. And again, we have to make sure that our models will adapt over time to reflect that. And the final one is about the fact that in all these models, we always just look at a single outcome, like heart attack or stroke. In reality, if you think about your perspective as an individual, there are many different types of trouble that could happen to you. So heart attack is one of them, but another one would be cancer or perhaps hit by a bus. So you would typically be interested in all these different risks, not one of them. So that's what we call competing risks. And there are methods to deal with that, but they're still very preliminary. So let's summarize. We talked about the data revolution in health, about predictive analytics, about the question whether machine learning is better than statistical modeling, and about the differences between the two things, about causal prediction models, and about prediction with electronic healthcare records. Just a few conclusions from my talk. I think that most, probably all the methods, all the models that are used in healthcare practice today are based on logistic regression or closely related methods from statistical modeling. As far as I'm aware, there are no models based on machine learning used in clinical practice. I think there would certainly be areas where machine learning would have benefits, but they haven't made it into clinical practice. I think the benefits will not come from better predictive performance. There's no evidence that machine learning will yield better predictive performance than statistical models. But I think they could contribute to some of the other challenges that we discussed. So there's a need for prediction models that can reason about the effects of interventions using causal inference. We know that electronic healthcare records, the main source of information for these models, reflect informative observation processes and that we can use those to make predictions themselves, and that there are further challenges around longitudinal data, dynamic prediction, calibration drift, and competing risks. So I'd like to thank my collaborators in these various pieces of work, and thank you for listening.